Thank you everyone for joining us for this webinar on WebSockets, what they are and why they matter, presented by Ian Craigie. My name is Laura Lawrence and I'm the Global Marketing Director at Hartmann. Just a few things before we get started. Everyone on the call is muted to keep down noise levels during the webinar. However, there is a chat function where you can submit questions to the presenter and we'll try to answer as many questions as possible at the end. This webinar will also be recorded and the link will be made available a few days after this presentation. We do have a number of other webinars taking place over the next few months for audio, lighting, video, and control, and we'd like to encourage you to take a look at the different webinars in our Learning Sessions workshop series on pro.hartmann.com, as well as visiting Hartmann Professional University to see our many on-demand and certification courses that are available to you for free. And now I'd like to introduce you to my colleague, Ian Craigie, the presenter for today's webinar. Over his long and varied career, Ian has worked as an audio engineer on Grammy Award-winning projects, a residential AV integrator, and an independent AMX programmer. In 2016, after an 11,000-mile motorcycle trip across Europe and Asia, Ian became a technical trainer for Hartmann Professional University. Now I'm going to pass the mic over to you, Ian.
Thanks, Laura. Hope everybody is doing swimmingly this Friday afternoon. Before I get into today's topic, I just sort of wanted to point out that in some ways it could be considered a companion to the MQTT webinar I presented a few weeks ago. The video for that presentation has been posted up on the YouTube channel, and everything you need to know about MQTT can be found there. There will be some peripheral references to that technology, so if you have any questions, it's there for your reference. Because this webinar is all about WebSockets. Well, almost all about WebSockets. I want to first review network communications in general, so we're sort of all on the same page, and then go on and identify where and why WebSockets fit into the equation. I'm then going to drill down into what WebSockets are and how they work, but it won't be too deep or painful, I promise. After all of that transfer of knowledge has been completed, we'll wrap things up by taking a look at what role WebSockets play in the audio, video, lighting, control space right now at this moment, as well as into the future. And I'll throw in a little bit of show and tell in the midst of that as we go through. So to start, I just want to ensure that we all can properly differentiate between a protocol and an API. Too often I feel, and I'm certainly as guilty as charged here as anybody else, that these two terms are incorrectly used interchangeably. Simply put, the protocol defines how a message is formatted, and the application programming interface, or API, defines what the message is. And they should be very much considered to be two distinct and separate things. And they then have a relationship to how they are presented. So with regards to actual network communication technologies that we run into, the simplest that we tend to find is the socket connection. That very much emulates the behavior seen across the old school RS-232 physical wire, which is to say a point-to-point typical persistent connection. The documentation provided for implementing a socket connection will define both the protocol and the API for this particular interface. The other flavor of network communication that we are certainly starting to see more and more of in our audio, video, lighting, control world is that of a web service, where the protocol is defined by a standard, such as Hypertext Transfer Protocol, HTTP, and then the documentation is just the API for that connection, because the protocol is defined by the standard. With the Roku set-top box external control service commands shown here, in addition to a standard protocol, the API is also well defined under the constraints of the Representational State Transfer Web Service, or RESTful API, where the requesting system is allowed to access and manipulate the textual representations of properties and actions at the device through a uniform and predefined set of stateless operations. If you have an interface with a device via a RESTful API, it's just a matter of time. We can then easily compare these two methodologies, the socket against the web service, in relation to the 7-layer open system interconnect or OSI model. And the big difference comes up at layer 7, right at the top, the application layer. With a socket, the standard layer 7 protocol is replaced by the protocol specific to the connected device or the service. Often the API and the protocol for the socket are tightly bound together to each other so as to be almost indistinguishable, to the point where API bytes are required to be escaped due to conflicts with protocol bytes. I'm not going to name any names here, but I'm sure you can, as to guilty parties. Whereas with a web service, regardless of what device or service we are talking to, the API message is simply passed into the top of the stack, where it has been encapsulated as per the defined standard protocols and forwarded down onto the next layer. And note here that the WebSocket protocol is just one of a number of different protocols that fall into the broad web services family, along with HTTP and ServerSent Events, SSEs, which we'll talk about in a little bit. So before talking about WebSockets, I probably should answer the question first about why not HTTP, and specifically in the context of a web browser, which is the native client for HTTP. Web browsers do not directly support TC/IP socket connections because it would be a massive computer security hole. The same origin policy, SOP, is a security mechanism built into modern web browsers. It stops scripts on one web page from accessing data on another web page. Without SOP, a script on a malicious website could request data from a company internal page, then send it offsite back to that original website. In that case, the additional ability to open raw sockets could allow a malicious script to also explore non-HTTP services such as email, DNS, or network file systems. WebSockets, however, are not subject to that same origin policy. The other issue with HTTP is the actual mechanism itself. HTTP is a synchronous communication protocol with a challenge response mechanism. Data is returned from the server only with a specific request from the client. Each data exchange also requires its own session, with each session requiring a new connection and a not unsubstantial amount of negotiation in order to be successfully established, especially if we add in the additional hurdle of the SSL or transport layer security handshake. There are two variants of polling found in HTTP, the default short polling or the long polling option. With short polling, we see a lot of requests that are then processed as they come to the server. The bad part here is if you need to be notified when the server event happens without any delay being incurred. Long polling has one request going to the server and a client waiting for the response to come across once it's resolved. So the traffic is, in effect, smaller and it's asynchronous-ish, but we end up with blocked resources and the connection still needs to be reestablished after the response is being delivered. With a WebSocket, the first step is, the initial step is to configure the connection, but that is a one and done deal. All commands and updates are then asynchronous after that. So in an ad hoc manner, the client sends its directive off across that single connection as necessary, and whenever there is an update at the server, likewise, it can then asynchronously propagate that information back to the client, all within the context of that single connection. So WebSockets. First and foremost, a WebSocket is an open standard for developing real-time applications. It allows for sending message-based data similar to UDP, but with the reliability of TCP. We find it originating in the HTML5 specification around about 2008, and then formalized as a standard in 2011. And it overcomes a number of HTTP issues: the lengthy handshakes, the header overhead, the synchronous nature, etc., with regards to delivering real-time data to web browsers. WebSocket is the only transport then that allows this bidirectional communication over the same TCP connection. Some of the key benefits that we find with WebSockets: that are certainly conducive to use in our AVL world. They're fully duplex, they're persistent, they exhibit very low latency. Extensibility is ingrained into the philosophy and design brief behind the protocol, and they are very easily securable through TLS. We also will find that WebSockets exhibit low bandwidth in comparison to other web services due to the minimal header weight that we will see momentarily. In terms of the process, all WebSocket connections start with an HTTP handshake initiated by the client to the server, requesting a connection upgrade to a WebSocket. Once established, the WebSocket connection remains on the same port referenced in that initial HTTP request, with port 80 and port 443 being the default ports for unsecure and secure connections, exactly like with HTTP and HTTPS, the same defaults apply. Once the connection upgrade is being confirmed, all communication continues as a persistent WebSocket until the connection is closed. Ultimately, the WebSocket is terminated by the server, either explicitly from a client request or implicitly through the client going offline. The handshake is a simple HTTP negotiation through a GETS directive with the required headers as shown, requesting a connection upgrade to a WebSocket. The server replies back with the HTTP 101 switching protocol response, confirming that the connection has been upgraded to a WebSocket. Of note here is the SEC WebSocket Key header value. This is typically just a random series of bytes passed as base 64 encoded string. The SEC WebSocket accept is the confirmation value hashed from the provided key and a known GUID string. This allows verification of communication to a WebSocket server and disallows caching proxies. It does not provide authentication, privacy, or integrity. Just FYI, the SEC prefix here follows the forbidden header name standard. These are forbidden, so the user agent remains in full control over them. Names starting with the SEC are reserved to allow new headers to be minted that are safe from APIs using fetch that allow control over headers by the developers, such as with the WebSocket protocol. With regards to extensibility, it's enabled through a couple of different mechanisms. First is the sub-protocol mechanism. So the WebSocket protocol makes no assumption about the format of each message. The payload is data agnostic. When specific formatting of the message is required, then the client and server must agree to implement their own sub-protocol to communicate this data. The WebSocket provides a simple and convenient sub-protocol negotiation API where the client can advertise which protocols it supports or would like to support to the server as part of its initial connection upgrade request, and then the server is then allowed to pick one of those protocols as advertised by the client. The IANA has over 40 currently registered official WebSocket subprotocols, which are expected to be implemented at any compliant server by mandate. Some of the more well-known ones, and again referring back to the MQTT webinar from a couple of weeks ago, we'll see WAMP, XMPP, AMQP, and MQTT all being real-time messaging protocols that are supported in this subprotocol API. You will also find some content-related subprotocols such as SIP and MPEG as well. The other mechanism where extensibility is implemented is through extensions, where subprotocols structure the payload of the WebSocket. Extensions actually control or allow for control over the frame and as well as modifying the payload. This provides a very powerful feature as it allows the client and server to implement additional functionality on top of the base WebSocket framing layer without requiring any intervention or cooperation from the application code. For example, the working group, which is responsible for the development of the WebSocket specification, actually lists two official extensions: a multiplexing extension for WebSockets that provides a way for separate logical WebSocket connections to share an underlying transport connection, and a compression extension which creates a framework for creating WebSocket extensions that add compression functionality to the protocol natively, for lack of a better word. With regards to security in WebSockets, like HTTP, we have a WSS WebSockets over SSL/TLS protocol that is encrypted, thus protecting against a variety of threats such as man-in-the-middle attacks. However, the WebSocket protocol itself does not handle any authorization or authentication. Practically, this means that a WebSocket opened from a page behind an auth doesn't automatically receive any sort of authentication or authorization. We need to take steps to also secure this WebSocket connection. It can be done in a variety of ways, as WebSockets will pass through standard HTTP headers commonly used for authentication. One common pattern that is observed that we see often is a ticket-based authentication system where the client contacts the HTTP server to obtain an authorization ticket. The server generates this ticket, storing it locally while also returning it to the client. The client opens the WebSocket connection and sends along this ticket to verify that it actually has been pre-authorized in effect to establish that connection. Another possibility is through the agreed-upon subprotocol after the connection has been upgraded to a WebSocket, if that subprotocol supports an authentication and authorization pattern. So I mentioned ServerSent Events earlier, SSEs. They are one of the known family of standards with regards to web services. And they are commonly referred to in conjunction with WebSockets. They are a standard. They were first found implemented in Opera 9. And their essential MO here is it allows for a client to subscribe to a stream of events generated by the server, receiving updates whenever a new event occurs. So they're asynchronous. But there's a couple of limitations with regards to SSEs, especially within the context of our audio-video lighting control space. First off, the data is limited to UTF, whereas WebSockets, we can pump in binary data. It's fairly data agnostic with regards to what the payload is. There is a connection, SSEs are subject to a much more restricted connection limitation with regards to the maximum number of open connections from a client to a server. With regards to SSEs, that limit is 6 concurrent HTTP connections per client, whereas with a WebSocket, you're looking at 1024 simultaneous connections between a client and a server. Probably the biggest restriction with regards to SSE is that they are monodirectional, in that the asynchronous nature only relates to the server sending data to the client. If the client needs to send a directive to the server, it requires a unique and independent HTTP connection to drive that directive from the client back to the server. And then finally, single ServerSent events are not extensible. If the application you're working on, if the requirements were to change, the likelihood is it would eventually need to be refactored using WebSockets, because WebSockets. When we take a look at the frame, and this is as deep as we're going to go, I promise. It's a relatively simple and lightweight header with regards to the frame and the packaging of the WebSocket. Each byte here has a well-defined purpose. The control byte section defines the context of the data in terms of its position in a series of frames and as to what type of data is contained in the payload. And as the saying goes, it wouldn't be a proper protocol if it did not include unused reserved bytes, and those requisite unused reserved bytes are found in this section. In the payload byte section, there is a mask enabler with the actual masking bytes following, and then the payload length value, which exhibits 3 different behaviors, defining the 3 different capacities that a WebSocket packet can hold. When set to a 5-bit length, the frame supports a maximum payload of 125 bytes of data. When we set that payload size to 16 bits, we now support a maximum of 64 kilobytes. That's the most typical deployment with regards to WebSockets that you will see. And then finally, we can set that payload length to 64 bits when the maximum data size expands now to 8 exabytes. Yeah, that's big. That's really big. And then the data itself is found in the payload, which may or may not be masked according to how the masking byte is set. Recommended best practices is that the mask is always applied. So as you can see, WebSockets are very much set up to move a lot of data around the network very efficiently. The persistent nature of WebSockets is manifested in a keep alive process referred to as the ping pong. And this ping pong allows the connection to be maintained even behind proxies, firewalls, and load balancers. The server initiates the ping and sends that ping message to the client through a WebSocket, which then replies with a Pong. If the client does not reply, the server closes the connection. And then the ping and Pong is just a manifest of a WebSocket frame with a specific opcode in that control byte right at the beginning of the header. From an implementation perspective, pretty much most modern standard-based languages have a readily available, if not embedded, WebSocket library that is very easy to implement. So, and as exhibited here, pretty much all of the standard third-party platforms in the audio-video control space: Python, Lua, C#, Java, JavaScript, even NetLinks. Hartmann's very own proprietary static scripting language. As we will see, it's actually very easily and very adept at handling WebSocket WebSocket classes, and there's even an open source library for the NetLinks WebSockets available for everyone to use. So it's show and tell time. So let's take a look here at a few things. So first off, probably the most typical place you're going to run into a WebSocket is likely with a device that has an HTML5 front end that leverages a WebSocket for the connectivity for control and feedback from that UI, that web browser-based UI, to the device itself. In that case, and this is sort of what we're looking at here, this is I've pointed to an echo test up at websocket.org, but this emulates that same effect where I would be interfacing with my device. There would be some sort of connection mechanism required. I could then manipulate it through some means, and when I was done, I could disconnect it. So, and again, this would be, if there was a DSP, we'd be manipulating the DSP blocks all through the HTML5 UI, and it would all be working all swimmingly, is the assumption. Within the web browser, specifically within Chrome, which I'm using, and the developers tool, I have the ability to actually inspect and audit what's actually happening with regard at the network down in that network stack, in that OSI layer. So again, if I was working with a device that had an HTML5 web interface, I'd bring up the developers tools, I would establish the connection, and I can now start tracing and evaluating and see what's going on as a way of informing my development workflow, so I can start to get an idea of what my output code is going to be required to look like, what the deliverable is, if I was creating a custom application for this particular device. I can then audit what was happening with the headers. So we can see here, this is the client request header. I've got my get message coming out, the requesting to upgrade, and with that upgrade being to a WebSocket, and then the key that's being passed along so it can then be hashed and returned accordingly. The response from the server, we can see there's the 101 being returned, confirmation of the connection upgrade. Here's the hash in the WebSocket accept value, and then finally a final confirmation that this connection is now a WebSocket. And at that point forward, I can now actually start monitoring what my messages are. If this is a device that was sending asynchronous feedback as I manipulated things directly on the front panel or from another client, I would see that information showing up here. So I can use the tools inside a web browser if I actually have an HTML5 interface I can leverage. In the case where where the device doesn't have an HTML5 web interface, there are plugins available for browsers which can emulate that missing UI interface. In this case, in Chrome, I'm using the simple WebSocket client plugin, and it essentially gives me the same effect as what we saw on that echo test, a very simple manifestation. I do need to get the URL. But I would just need to know where to point it at. I hit my open, and it's the same process. I now have access to the exact same information I saw before. And again, even if the device or service I'm working with doesn't provide an embedded HTML5 user interface or any sort of user interface, I still have the potential of using a web browser to start vetting what the application code, how the APIs are formed, how the APIs work, that sort of stuff. So I have within the developer tools, I can use this information to inform me in my application development. And of course, you know, if I was actually working with a third-party control platform that was then connected to a third-party device, you know, my browser tools no longer apply because I now need to affect packet sniffing, and I need to packet sniff between two devices that aren't me. So at that point, I'd be looking at implementing Wireshark, setting up a port mirror on the switch, and giving me access to the packets accordingly. Again, this is not a Wireshark class. This is about WebSockets. There's lots of information there about on the internet about Wireshark. But in this case, what I have is I've got a PCAP file capture from a different variant of the echo test site that we just saw. Unfortunately, this particular resource isn't available anymore, or it's been moved, and I haven't found where it's being relocated to. But this is an interesting examination of how a subprotocol works. And in fact, this subprotocol, its raison d'etre is for authentication and authorization purposes inside the context of the actual WebSocket application. But again, once you've filtered your WebSocket, or once you've filtered your packet trace for TCP is probably the easiest one to start with because this is all based on TCP. You eventually will identify the HTTP requests, and again, within the standard Wireshark dissector, we actually have access to decode a lot of this information. So here's my get. Here's the request for the upgrade to a socket. Somewhere down here, we'll have the key. And then finally, at the bottom, I see this. This is the client requesting the protocol be this XKZing handshake protocol. So this is the client requesting to the server, asking if the server happens to support this particular protocol. We can see the response, the HTTP 101 WebSocket protocol response back from the server that indeed the connection is being upgraded. There is the hashed acceptance key, and that here is the agreement that yes, this server supports the XKZing handshake. At this point, everything else is being done through WebSockets. And the way this particular, as it turns out, the way this particular subprotocol works, it creates standard HTTP formatted packets, and then passes them back and forth across as a WebSocket. So this is we're now looking at the process of the subprotocol running. Within the client, the first thing that happens is an uncredentialized GET again, it's a standard HTTP formatted packet, but it's an uncredentialized request for a resource at the server. I follow this TCP stream then. The server then responds back with a 401 unauthorized standard HTTP authentication authorization pattern. So then the client then responds with the required the basic realm authorization pattern where the credentials, the username and password are just base 64 encoded. And we can see, there it is. We can then see that upon that authorization and authentication pattern, that authentication being validated, and at this point authorization has been granted, and we see that it actually duplicates that same HTTP 1 WebSocket protocol handshake that we got that we would see otherwise. So there's a lot of with this particular sub protocol. There's a lot of duplication with regards there, but it's kind of interesting, you know, in terms of seeing how the sub protocol works, you know, and also then, you know, just sort of being able to demonstrate that, you know, that within the context of Wireshark, you've got access to a lot of this information as well. And again, from a development perspective, probably fairly handy, especially as you start auditing what's happening between the third-party control platform and the target device or service. So where are we going to see where do we see WebSocket applications right now and possibly into the future? Well, first off, HTML5. First and foremost, if you have a device or service that has an HTML5 front-end user interface, there's a WebSocket behind it, almost without doubt. And as these HTML5 interfaces are becoming more ubiquitous in our audio-video lighting control world, so are WebSockets. So I would suggest becoming familiar and understanding the technology behooves us all to be more efficient in how they are used. We're going to see them in services, in standard services such as MQTT. You know, and as I discussed in the MQTT webinar, with this technology, with this service being the most widely accepted transmission protocol for all things IoT, and with a decent chance that a large amount of that traffic is being implemented via WebSockets because HTML5, just as MQTT is pervasive, so are WebSockets from that perspective. We see it with devices. Hartmann released the DCP, the BSS DCP 555 not all that long ago. And in parallel with a TCP connection was a WebSocket connection. The WebSocket connection that is documented is actually the same is the exact same WebSocket and API that the HTML5 web page for this device uses. So it sort of went hand in hand. That became available as a control interface for that particular device. Interestingly enough, the DCP 555 uses the pre-authorized ticket variant of the authorization and authentication pattern, where you need to request a session and the username, the credentials are passed in through a URL encoding pattern to the server. The server returns a JSON ticket session object. That session object needs to be passed to the WebSocket server to validate that authorization is actually being granted. And then finally, we're also seeing this in large-scale building management and industrial control platforms like Siemens Mindsphere, where WebSockets become a de facto interface communication protocol and the de facto communication protocol. And again, so my expectation is that, you know, as the hardware that we work with mutes into more and more web services-based communication, that WebSockets will start to play more and more of a pervasive role and critical role as we go forward. So for those of you who, if this is one of the first of these that you've hung around for, you're not familiar with Hartmann Professional University, pro.hartmann.com/training. We've got hundreds, if not thousands of hours of content up there. It's all free, it's all on demand, and it's lots of information up there. We also offer certification streams across a number of technologies: audio, control, video, network AV, lighting. There's specified certification streams for all of those. Also, Hartmann Professional University, I believe, is still the single largest provider of, from a manufacturer perspective, of AVIXA CTS RUs. So if you're looking to bone up on it, if you're collecting RUs, that's a good place to go and do it. And in fact, we actually have currently in rotation 5 classes that we usually give in person in classrooms. It's the exact same content, the exact same instructors, the exact same time frame. So they are 1- and 2-day full-day sessions. And as you can see, that if you sit in through all 5 of them that we are currently offering through Zoom sessions right now under current conditions, you will garner more than enough AVIXA RUs to satisfy this 3-year period renewal. So if you're looking for RUs for renewal, this is the place to come and find them. We'll gladly help you out there. That's about it. I have, if you're interested in the NetLinks project that I did the demo off of, my contact information is here. I have an export of that available. Within that export package is also that authentication pattern with the XKazing handshake. So I actually show how NetLinks can easily support that authentication and authorization pattern. There is also an example project of connecting to the DCP 555 through NetLinks and WebSockets. And there's also an export of the open source library that's available from GitHub. And I should have done this before, but I have to very much thank Mr. David Vine from Australia. If he's watching, David, thank you. I have made full use of that library to great effect over the last few years. And again, you can Google up NetLinks and WebSocket and find the GitHub repository very easily. But other than that, I'm here to entertain any questions anybody might have regarding WebSockets.
Okay, we do have a question. Is HTML5 being used for touch panel user interfaces?
Well, yeah, at Hartmann, absolutely. The SDSI panel builder control product is all HTML5, CSS, JavaScript.
Okay, and then we did have a question asking if this recording would be available. Yes, all of the webinars are recorded and they're put out onto our YouTube brand channel. There's also a full Hartmann Professional University YouTube channel where all of the webinars can be found consolidated there. We have another question. Are there any courses for HTML5 and JavaScript?
We have, yeah, so one of those 5 classes that we're running, let me just back that up a second, oops. The MP132 JavaScript programming class that's available, it's utilizing the SDSI panel builder IDE, but it's a lot more focused on JavaScript more necessarily than the actual IDE. So certainly that would be a resource. There's also a little hour-long sort of precursor that goes along with that as well. So we do have some HTML5/JavaScript content.
Okay, another question. Any chance that HTML will ever be used on Hartmann NetLinks panels?
Well, it is right now. So if you are using a SDSI control environment and you would like a panel in the room that is an HTML5 JavaScript panel, we use the current Madero panels and we put them into web browser mode, and that's an HTML5 UI on a NetLinks, on an AMX Madero panel.
Okay, it looks like those were the questions that came in. So Ian, thank you so much for the presentation. Ian's contact information is up on the screen, so if you think of additional questions, feel free to reach out to him. And as I mentioned, the other webinars are available on pro.hartmann.com if you're interested in seeing the whole upcoming calendar. So thanks everyone for attending and have a great weekend.